Hello students, welcome you all. Now today I will explain the structural elucidation and synthesis of androsterone. Now after the discovery of cholesterol, many other steroids were discovered. And one of the steroids that was discovered by using this cholesterol nucleus, that was the androsterone. Now let's see the structural elucidation of this androsterone. So if we see the structure of this androsterone, it is like this. So this androsterone, it contains the androstane nucleus. It contains the androstane nucleus. So this is the one of the basic steroidal ring, and in this basic steroidal ring, these two are, this is C17 nucleus. This is C17 nucleus, and these two are the angular methyl group. And using this, adding these two angular methyl group, we get the C19 nucleus. Now here we have the hydrogen atom, which is alpha hydrogen atom, and at this position we have the alpha hydroxyl group. Okay, and now at this 17th position we have a keto group. So this is the androsterone structure. Now here we can write the hydrogen, which is below the plane. Here hydrogen is above the plane, and here hydrogen is below the plane. So this is androsterone structure, and it is C19. This is C19, which is the number of carbon which is present in endostane nucleus. So what I told you in nomenclature of steroids, so first is the guanine nucleus. What I told you, first is the guanine, one of the derivative of the steroidal nucleus. Then I told you after guanine, astrane. So guanine is C17 nucleus, astrane, this astrane is C18 nucleus, and then pregnane, another alkaloid, another basic alkaloid, basic steroidal ring derivative. This is pregnane, it is C19 nucleus. After that endostane, this is C21 nucleus. Sorry. After C18 we have endostane, which is C19 nucleus, and then pregnane is C21 nucleus, choline is C24 nucleus, and cholesterol is C27 nucleus. So cholesterol is C27 nucleus, and we have already discussed the cholesterol having the C27 carbon atom. So this is the structure of androsterone, and having C19 means the number of carbon atom present in androsterone is C19 carbon atom is present, or it is a androstane derivative. So let's discuss the structural elucidation of this androsterone. Now if we see this structure, then what we have to prove in this structure? So one of the things that it contains, this androsterone nucleus, it contains the basic steroidal ring, okay, and then after this it contains the keto group at 17th position, and this OH group at 3rd position. Now if we'll see, this is the first one, second, and this is 3rd, this is 4th, and this is the 5th position. So here in this case, this third position is the alpha position here. So this alpha position means 3 alpha, we can write it 3 alpha, and this is 5 alpha. This is 3 alpha and 5 alpha. So we should remember in androsterone structure that at 3rd position the OH is below the ring. OH is below the ring, or it is 3 alpha position and it is 5 alpha position. Now if it is this 3 beta, if this at third position OH is above the plane, or we can say 3 beta, then structure becomes different, and that structure is for the epi-androsterone. So but here we have to prove the structure of androsterone. Now, so if we see, first of all, if we see this molecular formula, then molecular formula for this that was determined, it is C19, and if we count the number of hydrogen atom, then it is 30, and number of oxygen atom is O2. So this is the molecular formula that was determined. After this molecular formula, if we determine the double bond equivalent, then double bond equivalent, that is that comes out to be 19 number of carbon atom minus number of monovalent atom, that is 30 divided by 2, and number of trivalent atom is 0. We don't count the divalent atom in the double bond equivalent formula. So 19 minus number of monovalent atom divided by 2 plus 1. So this comes out to be, this is 15, and 20 minus 15, that comes out to be 5. So dBe is 5. Now if we see here, if we see the structure here, then this dBe completely matches with this structure, and because the 4 rings, we can see 4 rings are present, and fifth one is the double bond which is present. So that's in this molecular formula, this dB is coming to be 5, and which is the correct one. Now after this it was this androsterone, that is C19, H30 and O2. So when hydrogenation was done, or hydrogenation in presence of this platinum catalyst was done, catalytic hydrogenation was done, then it was seen that no reaction takes place. No reaction. It means therefore we can say that carbon-carbon double bond is absent in androsterone. Now when this androsterone C19H30O2, when it was treated with acetic anhydride, or if we do the acetylation, you can say, if we do the acetylation, then it was found that this OH group undergo acetylation and it forms the monoacetate. So formation of this monoacetate, this OH is converted into the ester. So formation of this monoacetate, it tells that what it indicates? It indicates the presence of one OH group. So presence of, that is therefore one OH group is present. One OH group is present. Okay, now third one, when this next one, when androsterone it was treated with, for the determination of this keto group, when it was treated with suppose hydroxylamine or phenylhydrazine, we can treat it with, or we can treat it with dinitrophenylhydrazine. Okay, DNP test may be done. So monoxime was formed. Monoxime was formed. So therefore, it contains one keto group. Okay. So now this one, when this C19H30O2, when it was completely saturated, as it contains one keto group, means one double bond, one pi bond is present in this keto group. If we completely saturate this molecular formula, it means we may add 2 hydrogen over here. So what we may get, C19H32, and or we don't require to write this oxygen over here. So this corresponds to the general formula CnH 2n minus 6, CnH2n minus 6. So this CnH2n minus 6, it corresponds to tetracyclic nature of this compound, tetracyclic, or we may get this tetracyclic or 4-membered ring from here also. From here we may suppose, if we find the double bond equivalent for this one, DBE for C19H32, then what it comes, 19 minus 32 divided by 2 plus 1, and it comes out to be 16, and 20 minus 16, that's 4. So it comes out to be 4. So it means this is completely saturated one. This completely saturated compound having this 4 double bond equivalent, it means this 4 DBE, it corresponds to the tetracyclic nature. Okay. Now next one, when this Androsterone, when C19H30O2, it was treated with selenium at 360 degrees Celsius, or it was distilled in presence of selenium at 360 degrees Celsius, then we get a Diels hydrocarbon nucleus, Diels hydrocarbon. So this Diels hydrocarbon, so the formation of this Diels hydrocarbon, what does it indicate? It indicates the presence of steroidal ring. That is, therefore, steroidal ring is present. Steroidal nucleus is present, and this steroidal nucleus, no doubt, it contains the four rings, and one of the substituent is present at the 17th carbon. Okay, then finally, so after getting these results, actually this was given by all this structural elucidation that was given by Butenandt. Well, the scientist name was Butenandt. Butenandt was the scientist who gave this structural elucidation, who proved the structure in 1931. Okay, now after this structure, the Butenandt gave the structure. On the basis of this, Butenandt gave the structure. So proposed structure that was given, by this Butenandt, so that was very much similar to this Androsterone. So only difference in this structure was the OH group, which was above the plane at this third position, and rest of the structure given was the same. Okay, so this was the structure that was proposed by Butenandt after the structural elucidation. This was the structure, and later on it was called as the Endosperm. Endosperm. Okay, so finally the correct structure of this Endosperm, the correct structure was given by Ruzique. So Ruzique, he gave the correct structure in 1932. In 1932 he gave the correct structure of this Androsterone. So for this, first of all, he took the cholesterol derivative. And when what he done, first of all, he took one of the cholesterol acetate. So cholesterol acetate that he took, that was Okay, so this is your this is 5 alpha cholesterol 3 beta. So this is 3 beta acetate. This is 5 alpha cholesterol 3 beta acetate. Now in cholesterol we know that one of the double bond is present at this position. One of the double bond is present at this fourth and fifth position. So here this double bond is removed and this cholesterol, that is, and now we can write it as a cholesterol, and at this third position this acetate group is present. That's why we may write the 3 beta acetate. Now, so how we may get it? Just the acetylation of this cholesterol, acetylation of this cholesterol nucleus on acetylation, that will give you the 3 beta acetate or 5 alpha cholesterol 3 beta acetate. Now this was, so what we have to synthesize? We have to synthesize the this structure. We have to get this structure. So we should get this structure. For this, first of all, it was treated with chromium oxide. So this chromium oxide, it will oxidize this one. So this carbon, this carbon will get oxidized, and that this carbon, being the secondary carbon, that would be converted into the ketone. In the same way, this carbon, that would be converted into this keto group to get the isohexyl methyl ketone. So this chain, that would be converted into isomethyl hexyl or isohexyl methyl ketone, and here we will get the keto group. And in the second, so first of all, so at 17th position we will get the keto group at 17th position. Okay. So 17th position keto group, and here this angular methyl group are already present, and we have here at 5th position is the 5 alpha position, and this acetate group in next, that is being hydrolyzed. So hydrolysis of this acetate group. So after this hydrolysis, so that would be converted into OH. So here this OH is, as we can see, above the plane, whereas in endosterone the OH is 3 alpha. So this is 3 beta. So this is the 3 beta that we should remember. In the same way, this is also 3 beta. So when the Ruzuke, when he took this cholesterol acetate, and if we do the oxidation and followed by hydrolysis, he got the epi-endosterone. So he got this epi-endosterone, further epi-endosterone. Now further he took the 5 alpha cholesterol 3 alpha acetate. So when he took this 3 alpha acetate, then he got the endosperm. So now what he took? He took the 3 alpha. So this is our 3 alpha, and this is acetate is 3 beta. Okay, so and rest of the things are same. This is side chain. Now in the same reaction, so if it was treated with chromium oxide, so first of all, what he did, he protect this OH group of cholesterol by this acetylation, and he got the acetate group over here, so that we may do the chromium oxide oxidation to remove this chain. Okay, otherwise if we don't protect this OH group of cholesterol, in that case this will get oxidized to keto. So that's why first of all it was get protected. After the protection, the oxidation of the side chain and this was done to get the keto group over here. Now, so now he got the Androsterone. So this is the Androsterone. So in Endosperm, one of the things that we should remember, the position of this OH group, which is alpha. This is 3 alpha and this is 5 alpha. So this is also here 5 alpha in Endosperm. So like this. Okay, so finally the Endosperm, the structure of this Endosperm that was proved by this, it's a synthesis, and that synthesis was given by the Sandheimer and co-workers in 1935. Okay, now let's see the synthesis of Androsterone. Synthesis. So that was given by Sandheimer and co-workers. Okay, the Sandheimer and co-workers. So for this, the synthesis was done by using from Endosperm, because the structure of this Endosperm that was proved. So that's why the synthesis, for the synthesis, Endosperm was taken, and from Endosperm, this Endosperm that was synthesized. So the synthesis is from Endosperm. Endosperm. Okay. Now, so how we can synthesize this Endosperm from Endosperm? So this is Androsterone. First of all, what we have to do, we have to add this OH here below the plane. So for this, first of all, that this OH above, which is present above the plane, that should be removed. So what strategy that was followed to synthesize this Endosperm? So it was removed, and when we do the next attack over here, then the next attack would be from below the plane. Okay, so for this OH group has to be removed, and OH group is not the good leaving group. That's why it was converted into the another good leaving group, that is tosylate. So for this tosyl chloride was taken in presence of pyridine. If we take this tosyl chloride, okay, then this tosyl chloride may be added over here. So you may see that this tosylate group that would be added over here, and what we will get here, OTS. Okay, now so this OTS being this good leaving group, and okay, now so this is being, first of all, it was treated with sodium acetate, and then acetic acid and acetic anhydride. So what it will do, it will now, this may now attack over here, and this will get removed. So one of the product that we may get here, that is OAC, which is now below the plane, and okay, so and plus another product that he got, that was now, so this OAC that will get hydrolyzed, okay, hydrolysis of OAC, that will give here the OH and OH and one of the H which is present over here. So this will be converted into OH, and this H and OH that would be removed, H2 that would be removed. After removing this H2, we will get the one of the double bond. Okay, so what this, how a double bond came over here? So this OAC that would be hydrolyzed and will be converted into OH, and the H which is present at this position, the H2 may be, elimination of H2 may occur, and we will get a double bond over here. So okay, now so this on hydrolysis, simply by hydrolysis we will get the Androsterone. By hydrolysis we will get the Androsterone. Okay, and now, so now this would be converted into, now this should be, this can also be converted into this Androsterone. So this is the Androsterone, and now how we can convert this double bond, converting this double bond into this OH over here. So for this, what we can do, first of all, it was this keto group that has to be protected. Okay, so why, I will tell you. So first, this keto group that can be protected by a diol. So that can be protected, that can be converted into cyclic acetal. So keto can be protected by converting it into the cyclic acetal, and for this either 1,2-diol may be taken, or 1,3-diol or thiol may be taken for the protection. So first of all, this is being protected. Sorry, here we have angular methyl group over here. Okay. So now, so this is being protected, and now the reaction, we may do the reaction at the double bond. After this protection, so this double bond, that how we can convert this double bond into the this here OH group. So for this first we will do the epoxidation. So epoxidation we may use peracid that was used. So this peracid that will convert this double bond into the epoxide ring. So it will convert this into the epoxide ring. So no doubt this epoxide ring that would be formed below the plane. Okay, so epoxide that would be formed below the plane, because to prevent this 1,3 diaxial interaction, this epoxide that will come from below the plane. Now it can be this epoxide that can be opened by using either acidification or using this lithium anemone. The reduction may be done, and this H minus, so that will come over here, and this epoxide ring that will be opened. So what we will get finally, so we will get here this OH over here, and okay. Now finally we can remove this, the deprotection may be done. So using this aqueous acetic acid, the deprotection may be done, and deprotection of this cyclic acetal, that can be done, and we will get the finally endosperm. So this is one of the method of synthesis of this endosperm, which was by Sandheimer and co-worker. So this is about this structural elucidation and synthesis of endosperm. Now in my next lecture I will take the testosterone. Oh, thank you.